This diagram shows the typical setup for a fission reactor. So uranium fuel rods consist of uranium that is ready to fission, and there are control rods that are used to control the K value for the reaction. Besides these two rod systems, there is a chamber that is filled with either molten sodium or liquid water under very high pressure, and this is all contained within a containment vessel. Then some of the either molten sodium or water under very high pressure, that is allowed to pass into a secondary chamber where there is water. The heat that is generated, because remember the fission products have a lot of kinetic energy, and that kinetic energy gets transferred into the liquid that surrounds the fuel rods, and that very hot liquid then is allowed to pass through this chamber containing water. So this is known as the heat exchanger, and you can see that everything that is touching the fuel rods is not allowed to touch the water. So this flows through pipes, and so that they always remain separate. And then the water is turned into steam, and then the steam goes into a steam turbine. So the steam presses against the turbine, causes it to spin, which causes a coil of wire to spin in a magnet and generates electricity. So then after the steam does its job, it passes into a condenser where there is yet another system of pipes that bring in cold water from the outside. Often this is some cold water source such as Lake Michigan. And the cold water is separate from the water that is going into making the steam and running the turbine. So this cold water comes in and it cools the steam, turns it back into water so that it can then be pumped into the heating chamber and used again. So everything in this chamber is enclosed in a concrete chamber itself, which keeps everything sealed off from the outside world. So this is another diagram with a little bit of animation showing how the fission reactor works. So you have this containment structure with the working fluid that is in contact with the control and the fuel rods, and then that working fluid goes into the chamber where there is water that turns it into steam, that turns the turbine, that turns the generator, making the electricity, and then the steam is turned by a condenser back into water so that it can recirculate and complete this process. So currently about 20% of the power in the US is produced by fission reactors. In fact, this is a picture of Cook Nuclear, which is not too far away from Andrews. And these reactors produce electricity, 20% of the total amount of power generated in the US. However, there are big questions concerning the future of fission in the US and really around the world. The fission reactors in the US are all getting old. Many of them have gone past what was initially thought to be their working lifespans, and there is a question as to whether they should be replaced with more fission reactors or whether we should increase the amount of fission reactors. The top candidates for replacement right now are smaller modular reactors that are safer than the ones we have. They have totally passive safety systems, which means if you turned your back on them and cut power to them, they would just shut themselves down. The control rods that stop the reaction would just drop into place. If you cut the power, they're often held up by electromagnets, and then they will cool themselves down and just shut down very safely. So they are thought to be safer than the ones that are currently in use. And there are some pros when you talk about fission power. One pro, a big one at the top of a lot of people's minds, is that they don't have any carbon dioxide emissions. You're not burning anything, you're generating heat by allowing the fission reactions to occur. They actually put less radiation into the environment than burning coal. Coal has within it radioactive elements like uranium. I mean, it's just in the ground. And when you burn coal, you're putting a lot of pollutants into the environment, including some that are very, very bad for people, particularly children. They lead to complications with asthma, and it's thought that thousands of deaths each year are a result of the pollution that is in part released by burning coal and other fossil fuels. So they are less polluting than a lot of the techniques we have for generating power currently. The big con, though, is where do you put the radioactive waste products? Currently, there is no long-term storage facility in the U.S. for the radioactive waste, for the unused uranium in these fuel rods. They are typically stored on site at the reactors or in regional repositories, but there's no long-term repositories in the US, and the same is true of a lot of other countries. There are also concerns with nuclear proliferation. If you have other countries that want to have fission reactors so that they can produce energy more cleanly, you have to give them uranium. And of course, uranium can be diverted into not so savory uses. Plus, the nuclear waste can also be weaponized, and that's not a good thing. And a third consideration is that ultimately uranium is not renewable. There's only a certain amount of it in the earth, and you have to mine it out, which can be a very dirty process. And the uranium, there's only so much of it, and once you use it all, it's gone. So that's another con to using fission reactors. So here's a question for you. In order to alleviate the likely near-term increase in energy needs, do you think it would be a good idea to build more fission reactors?